Welcome. My name is Helmut Graeb. I'm from Technical University of Munich, and I'm going to present the following slides on how we can learn from the implicit hierarchy within a netlist and extract constraints and rules and functions that can be used for the analog design process. The talk will cover three parts. The first part will be on getting constraints and rules out of the hierarchical structure of a netlist and look at it within sizing. The second part will be on extracting constraints and rules, not just from the structure of a netlist, but also from its inherent signal flow. And we will look at how this can be used for placement. And in the third part, we will look at how to extract constraints, rules, and functions from the hierarchical function within a circuit, and we will use that for modeling. So let's start with looking at the hierarchical structure and what it can mean for sizing. Let's start at the very bottom. Here we have a MOS transistor. It has a drain, a gate, a source. It has the gate source voltage, it has the drain source voltage, and it has the drain source current, IDS. The behavior of the circuit can be visualized here by this graph, which shows the drain source current over the drain source voltage, and it can be parameterized over the gate source voltage. Now, if we look at that function and look specifically at what we call the saturation region, we have this quadratic behavior of the drain source current independence of the effective gate source voltage. So that means the transistor in saturation region works as a voltage-controlled current source. The voltage that controls is the gate source voltage, and the current that is controlled is the drain source current. Now, this formula also has the threshold voltage over here. So we have to look at the effective gate source voltage. Then it has the drain source voltage over here. Lambda is the channel length modulation, because it is not completely constant. So there is a slight increase in the drain source current over the drain source voltage, which is captured by this part. Then we have the channel width over the channel length. And we have some more technology parameters, which we here simply put as a K. Now, if we want a transistor to work in this way as a voltage-controlled current source, then we have to guarantee that it is working in saturation. And this has to be defined and formulated, for instance, for the sizing process. Now, here are the formulas that have to be satisfied for the voltages across a single transistor to keep in saturation. So for each transistor in the circuit, we have to write down these three equations. But that's not all for a transistor. We have to take into account that there is a variation in parameters of this simple equation that is coming from the manufacturing process. Let's simply take a look at the variability of these four basic parameters, the technology parameter K, the transistor width, the transistor length, and the threshold voltage. Now, for each of these parameters, there is a variance sigma square that we have to take into account. And if we take a simple model by linearizing this nonlinear equation with regard to all these four parameters, then this equation tells us that the overall variance of the drain source current, independence of these individual variances, is obtained by taking the sum over sensitivity of the drain source current with regard to the parameter square times the variance and sum all of these things up. Now, if we take these two basic formulas from Lakshmi-Kumar and the Pelgrom model and insert that so first determine the gradients from that formula here, take this formula here, then we obtain this formula over here. This is the relative variance, sigma, of the drain source current, sigma square of the drain source current with regard to its nominal value. Now, what we can see here is that in the denominator we have the area, the width square, the length square, and here again the area. So in order to minimize the variance of the drain source current due to all these manufacturing variations, we have to make area, width, and length large enough. So here we have some more constraints that the transistor in saturation has to keep. And meaning width, length, and area making large enough does not mean here that we are looking for the minimum pitch values for a technology, but these values here have to be way larger than than the minimum values that we use in digital design. So a transistor is just a very basic component. Now we can look at more complex components, and first thing is we build pairs of transistors. So one very basic pair of transistors is the current mirror. Here we have the circuit over here. So the interesting thing is that this is a diode configuration. So the gate source voltage here is actually the same as the drain source voltage over here, and it's this. Both transistors share the same gate source voltage, and one can show that the current that is flowing into these two transistors in this configuration has a certain ratio. And taking the two formulas from before, we take the quotient of these formulas and get this thing here. Now, we want to have this quotient. It's a kind of design parameter. We want to have it constant. We don't want to have it influenced by the manufacturing process. Now, one thing we can see here from this part, we actually want to prepare a regular layout, right? So transistors are designed with layouted with fingers, interdigitated or common centroid. So to make this easier and get regularity, the lengths of the two transistors are the same. And then basically the current ratio that we want to design is determined by the relation between the two widths. Now looking at this here, if the threshold voltage would be the same for both transistors, there would be no influence. But in the manufacturing process, there is a local variation of the threshold voltage, which means that they are different. They are changing in a different way, which means this is influencing this ratio R. Now, if the gate source voltage is too close to this threshold voltage, especially in the denominator over here, then it may have a large influence on the ratio. So we want to have the effective gate source voltage large enough, right? Not below a certain value. And the next thing here is, depending on the circuit around this current mirror, the two drain source voltages will not be the same, but also this would influence the current ratio. Now, to minimize the influence of the difference in drain source voltages, to minimize the impact of the drain source voltages, the difference between the two of them should not be too large. So we have to give an upper threshold for that. So again, for a current mirror, in addition to these constraints that we set up for the individual transistors, we have constraints that have to be kept for the current mirror. Good, we have more than just a current mirror. So how many transistor pairs could we build? So a transistor has 3 pins, and the way how to combine these two transistors by combining at least 1 pin or 2 pin or 3 pins combinatorially, if this is the Bell number, gives us 203 different variants of transistor pairs we can have. Actually, only few of them have a design relevant function, and here we can see some of them. Here we have the simple current mirror we had before. We have something which is called level shifter. We have a differential pair. We have a simple flip-flop. And then we have things like voltage reference of 2 types, a current mirror load, a cascode pair, or something we could call mixed pair. And again, for maybe not all of these pairs, but for at least those 4 up here, we can set up individual constraints, actually, just like we did for the current mirror. Now we have to look for more complex groups. So this is something like, building pairs of pairs, or combining a pair with a single transistor and going up. This basically leads to different types of current mirrors, as are shown here. This is a cascode current mirror, 2 types of a Wilson current mirror. This is something we call 4 transistor current mirror. This is a typically used wide swing cascode current mirror. Now, if we take any of these current mirrors and combine it with a differential pair, we get what is called a differential stage. Now, in the next step, we can create a hierarchical library how these transistors to pairs, to groups, to the differential stage are built up in a circuit design process, in the structural design process, and we can formulate it in a computer way. So here we have written a differential stage consists of, as we said before, a differential pair and a current mirror. A current mirror is either a wide swing current mirror, a cascode current mirror, and so on. A wide swing cascode current mirror, for instance, consists of a cascode pair and a voltage reference. A cascode pair consists of two voltage-controlled current sources, and a voltage-controlled current source is a transistor. So here we know how to formulate in a suited way for the computer the composition of, well, a simple differential stage. Now these are the number of sizing constraints noted that we have for different blocks. You know, we have written down 6 rules. We have looked at them for the transistor as a voltage-controlled current source. We have looked at the simple current mirror, and so on. So what do we do with this? Well, if we get a netlist, usually we get it in some kind of, flat way. But in a way, we look at the netlist, we take our hierarchical library of structural blocks. Now for each of these structural blocks, we have written down the, well, let's call it sizing rules, constraints, and we have a hierarchical library of these rules. Now we go into the netlist, we search for these blocks that we have seen before, and once we have identified them, we instantiate from this hierarchical library the corresponding constraints and sizing rules, and then we have all of them automatically. Now, the structural analysis for these building blocks mathematically is a search for subgraph isomorphisms, and we do this bottom up, right, from transistor to pair and so on. So let's take an example here. So this is some kind of folded cascode op-amp, I think 22 transistors. Now, what does the algorithm? It goes through the library and it looks for the pairs. So here we have a voltage reference of type 1. Over here we have a current mirror load. Then we have 2 transistor current mirrors, right? This one together with this one is a current mirror. This one together with this one is a current mirror. Those two, and those two. In correspondence, as this is folded cascode, we have level shifters down here. Oh, this one with this one, this one with this one, this one with this one, and so on. And then we identify a differential pair. Well, the algorithm does. So now we have found all transistor pairs. Now we build groups, pairs of pairs, and so on. And in that step, what we find next is a 4 transistor current mirror, current mirror banks. This is something we can identify, level shifter banks, and finally a cascode current mirror. Here's one, and this one is one. So these are the pairs we find, and well, might be fun. We can also identify a cascode current mirror bank, but finally we find this differential stage. And overall, we set up automatically 30 equations for this circuit and 160 inequalities. So overall 190 sizing rules. And of course, we don't want to do this by hand. So the crux for circuit design, or for circuit sizing in this case, is that you do it automatically by such an algorithm. The interesting thing are the 30 equations. That helps a lot because we have, I think, 22 transistors. This is 44 overall design parameters, width and length. And of course, we do not change them, all of them individually, but actually 30 of them depend on the other 14. So we only have 14 independent widths or lengths in this circuit. Good. Now, what does it mean to have these constraints? So let's take a look how the sizing process is influenced by these constraints that we have. Let's again take this typical example here. And what we have done here is we have first determined a sizing of the circuit once without using these constraints and ones with. And you know, this is the difference if you go to an automatic optimizer, to a tool, and you don't have these sizing constraints, right? Then you would do it this way. When you have them, but you need this additional effort and this knowledge to set them up, you get a result like this. And what do we see here? This is the gain over the supply voltage of the circuit. So here we have the minimum supply voltage, the nominal supply voltage, the maximum supply voltage. So as we can see here, approximately the nominal gain is the same. And we size the circuit for the nominal supply voltage, either additionally using the constraints and then using them not. And now we see over the supply voltage here, when we do afterwards, we do a sweep over the supply voltage. When we haven't used the sizing rules, the gain, disappears, we could say. It fails. It violates the spec. But if we use them, it's pretty insensitive to the gain. And this has to do with, with considering all these constraints. The designer, if the designer does the sizing by hand, he or she knows what to do, but an optimizer doesn't know. The optimizer has to be told what to do it, intelligently. But it's not just that the circuit robustness is better, we also get a better efficiency and convergence of the sizing process, right? Not using constraints, it took, in this case, 126 simulations overall, and using the constraints, it was faster, the 45, right? Mathematically, more constraints is not more effort, but it is a help to guide the sizing process. It makes it easier for the sizing process. And actually, in the end, after looking at these sizing process, you can also see which constraints are satisfied and which, are at the border, which are easily satisfied and which are really active. And very often, if you start an optimization process, an automatic one, and you don't use these constraints, that is why here it says infinite, it doesn't even converge at all. So the constraints are really crucial, and the interesting thing is we should automatically know how to extract them from the circuit netlist. Okay, I should add at this point here, it's all not that easy with this structural analysis. So one thing that we have to do here is, if we find a transistor and other transistors, one transistor could be part of two different types of pairs. And it shouldn't be in two parts. We have to decide which one is it. And we need to set up some kind of arbitration rule, something like if a transistor is part of group type A, it cannot be part of group type B. So it is A in the end, the pair. Another problem is that what I have presented before is just one way to compose, for instance, a pair of pairs. Here, the Wilson 2 current mirror, right? So this is the overall shape. It has usually what you could do it. If you do it like this, you can say that's what we defined before. It's a current mirror, and on top of that, there is a level shifter. This makes it easier to set up the sizing rules, but actually you could also define it in this way, like these two groups. This is a mixed pair, and you can combine it with another mixed pair, and still we have the Wilson 2 current mirror. This way of composition or decomposition may be better if we go to guide the placement. So it's not that easy as I was showing before. There's a lot of ambiguity, and you have to consider that. Now let's switch gears. Now let's not just look at the structure of the netlist, but let's also look at the signal flow through that structure, and let's see how this can be used for placement. So far we had constraints from building blocks, but now we are adding that there are constraints from symmetrical signal paths. Let's look at an example here. So down here we have a current mirror bank, and as we have seen before, there are matching constraints for this building block. Then we have a differential pair here. We also have matching within that building block, right? Both these constraint types are for building blocks and for constraints within the building block. Now, take a look at that. Here is the differential pair as input. So we have one input signal which goes over here through that current mirror down here to the output. At the same time, we have the other differential input, which goes from this over that current mirror, over that current mirror, and over here to the output. So now, as this is a differential signal, we want to have symmetry in order to keep the symmetry in our function. Those signals here should also go along symmetrical structures. Now these are constraints across building blocks, so which means those two should be matching, and the whole two things here should be matching. So this is another quality of constraints which come from looking at the circuit structure plus the signal path, right? This is not really like a signal flow analysis with transfer function, but we are looking at signal paths through the structure of the circuit. So what can we do with that here? Within placement, what we can do is we can create a placement plan from a constraint hierarchy. So let's again look at this part over here. That's the differential pair, those two inputs, and they go over these two current mirrors here. And now we define as a heuristic a priority of constraints. So the most important constraints are the matching constraints which come from symmetry paths. Then we look at matching constraints from the building blocks, proximity constraints, and then general symmetry constraints and proximity constraints which come from the netlist. So how does this kind of graph come from? This is a constraint graph. The N1 and 2 are these two transistors, P1, P2 are those two transistors over here. Now these were the symmetrical signal paths, so we have a matching constraint from the symmetry path between P1 and P2 and between P3 and P4 and N1 and 2. Then we have the matching constraints from the building blocks, right? Those two should match. This is the blue one here. Those two should match, the blue one here, and the differential pair should match, so we have the blue line here. Proximity constraints, we don't draw them here because they should all be proximity constraints are general ones which don't apply here. But we have symmetry constraints from the structures, and this somehow tells us that this is fully meshed, right? So we don't draw it. And then we have proximity constraints which simply come from the netlist, so it's which transistor is combined by a signal with which one. We just drop VDD and ground. So from this here, what we do now is we build matching groups over here from symmetry and building blocks, then we build symmetry groups and then proximity groups. So the first thing here is that we have the matching constraints. So this brings us that P1 and P2 should be a matching group, P3 and P4, N1 and N2 another matching group. Now building these matching groups, the constraint graph now for those three matching groups looked like this. So we still have, P1 and P2 is a group, P3, P4 is a group, and there is still, as a next thing, the matching constraint, the blue line between those two matching groups. The rest now is kind of, fully meshed, and now we additionally draw the symmetry constraints for them. So the next step now is looking at this graph. Okay, now we have to build a matching group from these building blocks. So this comes now, those two become a matching group. The graph looks like this. And then finally, okay, the next constraints which comes into place are symmetry constraints. So those two build a symmetry group. We might have more proximity constraints if there is a connection to some other part of the circuit. So now what we have is a hierarchy, right? So, okay, those two should match, which means, we should look first at them from the placement point of view. From the placement point of view, we should look at those ones here and then at those ones, and then we should go further up and combine them. And this is similar, or maybe even identical to how manual layout is proceeding. So what we do now in placement is, so this is kind of, it's not the same circuit as before, it's some kind of op-amp. We have a current mirror with a differential pair, builds a differential stage with another current mirror, builds the core, and then we have the kind of compensation and then some more single transistors to the output of the operational amplifier. Now we have built from the previously shown constraint graph, we have built this hierarchical group building for placement. We start bottom up at the bottom for the current mirror. In this case, we have a current mirror with 3 transistors. Now, what we do here is we enumerate all possible placements. This can be done because the number of elements is small enough. And we do this for all these basic building blocks here. So this is what we have. Now, what's the next step? Now, what we do next is we set up or we code the placements of these different enumerated placements in form of a B star tree. And as we have different placements, we have different aspect ratios, and we can put up a shape function like this for the current mirror and the other ones as well. And for each point here, we have a possible placement, and we code that placement as a B star tree. And now Martin Strasser has found out that we can now combine 2 of these enhanced shape functions with their B star trees by a formulation of a horizontal and vertical addition of the shape functions of these B star trees. And this is done bottom up. The nice thing is the white space, when you go up from these 2, the white space existing here is used, right? You combine them and you automatically compact them. And Martin Strasser has shown that while going up, the placement constraints from a lower level are provably kept for the next level, plus the additional placement constraints that you have there, right, for symmetry and so on. So we start now. For those 2, we combine, get the shape function, then we combine it with this one to get the shape function here, then we combine it with this one to the overall shape function, and then we can look at each of these dots here and get a specific placement with inherent consideration of all the symmetry and matching constraints, alignment constraints, all the constraints which are there for the placement. Of course, you have to consider them, or you have to set them out automatically, not part of this talk. And usually, this placement plan, it's not even optimization, it's a construction, is done in seconds to a minute, which means usually as a layouter, you look at this here and just say, I don't like this and that, I need another constraint. You can add that manually and just restart the whole process with an additional constraint. So this is a very nice example how, getting the constraint, getting the knowledge about symmetry with design knowledge, looking at the netlist, setting it up automatically, we can create a placement process out of that. Okay, once again, for the last time, let's switch gears. Now we will look at how we can get constraints and rules and even performance function from looking at a hierarchically built up of the netlist with its functional blocks. And we will use that for modeling. Now, what is a functional block? What do we define as a functional block? So a functional block is a block that represents a certain basic analog function that is needed within an analog circuit to get to the overall function of the circuit. Here on the left, we have an example. So VB, it's a voltage bias. This is a function. A voltage bias has the function to convert the current into this node in here into a voltage at the node, at the output node out1, or maybe at 2 output nodes. This is an example. A voltage bias, for instance, is part of a current mirror, but it's a function. The function means now we have to implement the function, and here on the right we have different implementations by transistor netlists for this function. The interesting thing here is, depending on the implementation, this block here, this functional block, may have a varying number of pins, right? There may be an inner pin, there may be a second output pin. It depends on the implementation that's given here. And it's getting more difficult now compared to the structural blocks before, because as we can see here, of course, this is, the design freedom that we have for one functional block. We may have a number of structural implementations, but it's also the other way around. A certain structural implementation that may refer to different functional blocks that we have, not just one voltage bias. It may be different. So it's not so easy, but it gives us more, well, more power actually in the end. So here is an example. It's a functional block library for a very simple one-stage op-amp. It's just one way of doing that. The colors show how one block from one hierarchical level is used within another hierarchical level. So here it starts with capacitor, diode transistor, normal transistor. And then here we have the voltage bias from before. It's in blue, so it consists of a diode transistor and a normal transistor. That's the color. So the voltage bias in blue is used, for instance, as used within a so-called load part, and it is used within a so-called bias. Well, the load part in turn, this the green thing here is a load part of an overall load, right? Here with two load parts, here with one load part. The load is used within first stage and so on. This is nothing more than picking how a structural implementation of a circuit is built up, well, both bottom up and top down in a hierarchical way, right? In the end, you end up here with a one-stage op-amp with a bias and with a first stage, for instance. Interesting. What can we do with it? Well, there is something in addition. Now, for this library of functional blocks, right? We have devices, the transistors, we have these current mirrors behavior, we have this amplification stage sub-blocks and the amplification stages, and finally the op-amp, right? Before we had to the amplification stage, we had this kind here, and the op-amp, 4 levels. Let's just, yeah, before. Now, we can not only set up the constraints like symmetry constraints, but also behavioral constraints for the current mirror and so on, output voltage or offset, for instance. We can also set up intermediate performance equations for the blocks, and then in the end, the overall op-amp performance equation. So just to show the example here, the open loop gain of the overall operational amplifier is a formula in which a parameter is used which is output of a formula for an intermediate performance equation of an amplification stage, which is the stage open loop gain. And this in turn depends on the amplification stage subblock transconductance. So each equation here has input and output, which are then output and input on a lower or a higher level of abstraction. For instance, well, the stage output resistance is a formula which needs the output conductance. The unity gain bandwidth uses the transconductance and the net capacitance. This can be used to somehow even set up a structural synthesis and sizing process based on these analytical equations. The advantage of this is that you only create circuit implementations which are technically meaningful, right? You don't create something which turns out to be odd in the end, because if you look at it, it doesn't work. You right away only create structures that are good. We have dealt with that. But here we want to do something else. We want to use that method to create op-amp structures to get a large sample size. So what we have done is we have used this algorithm for structural synthesis and sizing to create a whole set of implementations for this example of 4 performances: gain, slew rate, phase margin, transit frequency, within these given bounds over here. So we have created, something like more than 500 different structures. These structures have been characterized or looked at specifically for 20 different structural building blocks: transistor pairs, various current mirror types, as we have seen before, and typical analog inverters. These are the structures at the end before the output, right, to amplify. And we have done the following functional blocks. So we have the load, we have the transconductance, the bias, and the op-amp stage. Now we have characterized all these things for not just the 500 op-amp structures, but for each op-amp structure, 150 different sizings for the various specs. So overall, we have something like, you could say more than 100,000 designs with all these details. We have the structure, we have the hierarchy of these building blocks. As information, we have the hierarchy of these functional blocks. and we have the sizing and the performance value of all these. So this is a kind, it's as if we have collected a lot of op-amp designs, well, very simple ones here only. So what can we do with that? So one thing is we have tried to cluster these. So we have created 20 different clusters covering, all these. This is the performance space for gain and slew rate that was defined with lower and upper limit before. Now we have 20 clusters to build 20 different specification groups within that. And the idea is within that cluster so that you don't have to try if you come up with a certain and then we have built the neural networks, of course, for these clusters. So what you map is you want to have a certain performance, and then it tells you, oh, look, here is your cluster. Here is your set of circuits which are good for that. The point is we want to reduce the number of potential topologies we have to try, right? If we come up with a specification, it gives us a subset of all these learned implementations, and then we take a closer look at that. Now, how good is that neural network in doing that? Well, the precision and the recall was, well, more than 70%. It doesn't look really perfect. We want to have more than 90%, but as a first thing, it's a good thing, right? So more than 70% of the assigned cluster have been correct, and actually more than 70% of what we should have recognized was correct. Not perfect, but not too bad at the moment. Another very interesting thing we tried is we want to have somehow speed up the circuit sizing by doing it with a neural network instead of starting optimization. So what we did here is, actually Markus Leibel did it, the co-author, so I should not say we, you should say he. So we built a neural network for each functional block we have, right? That maps the circuit specification on the sizing. So now we did that for all our blocks, and actually maybe better not just the functional blocks, also the structural blocks defined before. So for instance, here we have a current mirror. So the output of that neural network is the sizing, right? The sizing of M1, M2, the width and length of M1 and M2. The input of that neural network is which functional and structural blocks do this thing belongs to, yeah. And then for each of these structures, we have a reference block just to make it easier. So what is the circuit performance and the sizing of this reference block? And the input is the circuit specification. So actually this was done over all these kind of 100,000 designs, different op-amps and so on. But when a circuit specification comes in, then this neural network tells you, okay, that current mirror within your circuit should have this and that sizing, independently of the other parts. And this is an interesting thing. So now when you start with the overall spec, you go in parallel into the different functional blocks. And this is shown here on the right for a core of an op-amp. And then the neural network tells you, right away tells you what is your sizing. So here we have this example. It's a core of an op-amp. We have and this is interesting, right? The green thing here is what it is on a functional level. So on a functional level, this is at the load. On a structural level, it's a current mirror. On a structural level, this is a differential pair. On a functional level, it's transconductance. This here is a current mirror on a structural level, but a bias on the functional level. Now, coming in with a specification. So this is the kind of thing we wanted, right? For the gain, transit, frequency, phase margin. This is what we would like to come out. And the expected things, from looking at the real sizings that we have, these are the width to length ratios in black for all the transistors. And now this is what the neural net predicted. And you can see for the differential pair, pretty exact. Not so good here, not so good here, but I mean, you do it independently, right? Just by ignoring the rest. But you can see, oh, the gain is not so bad. Well, not so nice. This is also very good, not so bad. Not so well, not so good, not so well. But you can see, it's not to show that this was a good idea, but it's a good idea to use this knowledge of structural blocks and functional blocks to also improve your, in this case by neural network, improve your modeling and topology synthesis by neural networks of your design. So that was the third example of where structural and functional blocks and knowledge are good. So coming to the conclusion, so you can build hierarchical libraries of maybe not canonical, but basic building blocks, and you can create generic sets of constraints, rules, and functions for these building blocks. And with this, you can and should create an automatic setup of the constraints, rules, and functions for your circuit. And this is really crucial for synthesizing and layout, and maybe even as important as the numeric solution algorithm itself. So this is to conclude my talk. I just want to like to thank all the doctoral candidates which have or are contributing to this work here that is presented. And well, finally, here is a list of references for the things presented here. Thank you.